Alright, here's a not too hard of a problem that I was making really hard for myself for some reason. Um, I don't know what's going on with this bar down here. I'm just going to leave it alone. So anyways, first thing we're going to do is we're going to write row as this, where row I is irreducible. So we basically decompose it into its irreducible representations. And so then what happens? We have 1 over the order of capital G, which is lowercase g, because Serre somehow thinks that that is logical. But I guess it is nice that you don't have to put brackets around g every single time. But I'm so used to using little g as like the go-to element of capital G. But what are you going to do? So we have this, the sum overall. No, there I go again. S and G of chi rho of S. I'm including the row down here because what we're going to do now, well, not quite yet, but it's coming. S and G, chi rho of S. Obviously, we can multiply this by 1. However, we know that 1 is the character, no, 1 is the trace of the irreducible, of the unit representation. So chi 1, I use boldface 1 to denote the unit representation. Or trivial representation, whatever you want to call it. And because the trivial representation, you plug in any element of capital G, and you just get the identity transformation. And so that's just going to be the matrix given by, like, you just have like 1 in there. And so of course the trace of this is 1. Of course, if it's like a larger vector space, oh no. Yeah, it's just 1. That's what the unit representation is. It's always, you always get 1. And so then what is this? But this is, by definition, this is equal to the inner product of chi rho with chi 1. And so then now, let's see, I believe that using parentheses and these angular brackets are the same thing when you're doing it with characters. Oh, right, yeah, because they're class functions maybe, or something like that. I don't know. I don't quite remember. But I know that when I was doing this in class, I used the angular brackets and it worked. So so don't be worried about the discrepancy between here and here. It's okay. But okay, so now what is this? What do we know about this? We know that this is the multiplicity of the unit representation in row. That was one of the theorems from this section. And so that's precisely the number of row i's which are isomorphic to the unit representation. Right, isomorphic as representation. So it's basically all the irreducible components of row which are basically the unit representation, which is what they mean when they say that this is the number of times that row contains the unit representation. So that does it. That's pretty much the problem. This solves the exercise, but there's more. because, and I might as well include it. We had to prove this more in class, but it's easy and it uses stuff from previous in this chapter. Furthermore, 1 over G sum over S and G chi rho of S equals 1 over G the sum over all G, all S and G. Now this is using one of the previous exercises, 2.2. Using, I'm going to write 2.2 here because we're using exercise 2.2. This sum is actually equal to the number, well, this chi rho of S is equal to the number of elements of capital X. Oh, we're not talking about, we don't have a group X here. G is not acting on a group X. And furthermore, if G acts on a set, on a set X, then 1 over G sum over S and G chi rho of S is equal to, by exercise 2.2, 1 over G sum over all S and G of the number of elements of X which are fixed by S under the action of capital G on capital X. But this is equal to G mod X, because the second one is by Burnside's lemma. And so, let's see here. Burnside's lemma, that's a thing. I don't know if Jacobson actually talks about it in his textbook, but you can look it up if you want. But yeah, so this actually gives an interesting thing where if you have capital G acting on a set capital X, then this the number of times that row contains a unit representation is actually equal to the number of distinct orbits of G on X. Did I write this correctly? Should this be G? Should the slash be that way? Yeah, because I think this slash is for like exclusion. And I think this, well, wait, is it G mod X? Not really modding out by, well, I have it on my paper as this, as going this way, and I'm going to guess that this is just some notational thing that I learned, because I guess it doesn't really make sense to talk about the set G exclude capital X, because X is not a subset of G. X and G are completely different things. They're not even the same type of thing. Like, G is a group and X is a set. All groups are set, but like they don't, there's nothing similar about them. So it's not like one's a subset of the other. So it wouldn't make sense for this to be like set exclusion. So, but whatever it does refer to, you can just look up Burnside's lemma and use whatever notation you find or whatever works for you. But it's the number of orbits of G on X that I have written down. That's in the problem statement, the way it was stated when I had this exercise. So anyways, sorry for, I guess I added like a lot of time to that video by just using that quick, by saying that quick thing at the end there. But the main thing is that we've got this computation in the first 3 lines here, and that completes everything that was asked in this exercise.